The second of the small gas laws is Charles' law, and this looks at the volume-temperature relationship. I always think this one's quite interesting because Charles had a very interesting hobby that led to his work with volumes and temperatures of gases. Does anybody know what that was? Okay, someone had mentioned earlier today going to Albuquerque, New Mexico for the Hot Air Balloon Festival. Charles was actually a hot air balloonist, and that's how he did a lot of his early work studying the relationship between the volume and the temperature of gases. So, pressure and temperature of a gas, what am I doing here? Volume and temperature of gas, not pressure and temperature. The volume and the temperature are directly proportional if we hold the pressure and the amount of gas constant. I got those two switched around when I typed this. So we say when we're looking at this that volume is directly proportional to temperature. So we could say in chemistry, getting rid of the proportionality, volume is equal to the temperature times some constant C prime. We call it C prime just to let you know that it's not the same as C, the Boyle's law constant. So now the one thing we have to remember here is that the temperature has to be in Kelvin. So you don't ever want to plug in a Celsius temperature. It must be converted to Kelvin before you plug anything in. And now we can rearrange this to say that the volume divided by the temperature is equal to the Charles law constant, C prime. Now, just like Boyle's law, we don't always have these constants readily available. Because the constants aren't available to us, we find it convenient in chemistry to put things in a two-point form. We know that V1 over T1 is equal to C prime, and we know V2 over T2 is equal to C prime. So if they are equal to the same thing, then they are equal to each other. So V1 over T1 equals V2 over T2. And we now have the two-point form that we'll use over and over of Charles' law. So you'll find that this is just like doing Boyle's law problems. This time we're dealing with volume and temperature, and we have to look at this, and again, any volume units are okay. It can be milliliters, liters, gallons if you wanted to use an English unit instead of a metric unit, but you do have to make sure that this is Kelvin temperature always. Let's look at an example. What is the final volume if a 275-liter balloon is heated from 20 degrees to 40 degrees Celsius and the pressure is held constant? Well, my original volume, V1, is 275 liters. My original temperature is equal to 20 degrees Celsius. I know that I need this in Kelvin, so I add 273.15. So I have 293.2 Kelvin, preserving significant figures going out to the tenths place. And my new volume, V2, is my unknown, and my new temperature is 40 degrees Celsius, which is converted to Kelvin. We get 313.2 Kelvin. So now I have all the information that I need. Now I just have to plug it in and do the algebra. So we know V1 over T1 equals V2 over T2. Since I'm interested in the new volume, I'm going to multiply both sides by the second temperature. So V1 T2 over T1 is equal to my new volume V2. So I plug in my numbers. 275 liters, my original volume, times my new temperature, 313.2 Kelvin, divided by my original temperature, 293.2 Kelvin, is equal to, on my calculator, 293.8 liters, But when I go back and check my sig figs, what can I report? How many sig figs? 3. So I round to 294 liters. So we do the math just like we did Boyle's Law. We have an algebraic relationship. We know 3 of the 4 variables. We solve for the 4th. Let's have you go ahead and do these on the boards with your groups.